Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be looking at Graham's Law and Dalton's Law of partial pressure. So if you have any questions, let me know. All right, so we're going to start with Thomas Graham, who discovered Graham's Law. He discovered that if you release two gases, the rate at which they move is directly related to their molar masses. So in other words, the way you can kind of qualitatively describe this is that the heavier the gas, the slower the gas is going to move. And if you have a lighter gas, that means that it's going to be moving faster. So this is typically called a rate of effusion, meaning that if you had like a can or something of gas and you punctured it, the speed at which the gas escapes from the can would be described as the rate of effusion of the gas. So like we said, that's called Graham's Law. And what you do is you use the following formula. So we have R1 divided by R2 equals the square root of M2 divided by M1. So R1 and R2 are the velocities of the different gases. And so the gases that we're looking at would be numbered number 1 and then numbered number 2. So R1 is the velocity of gas 1, R2 the velocity of gas 2. Now you take the square root though of m, and m in this case is representative of molar mass. So it's the molar mass of the second over the molar mass of the first. And remember, we're taking the square root of the entire thing. Also, just as a little side note, if you have the square root of something like this, you can easily just do the square root of the top part divided by the square root of the bottom part. You don't need to write it typically like this. And like we said, you just compare the molar masses to each other. So here would be an example of what one of those Graham Law questions might look like. So if equal amounts of helium and argon are placed in a porous container and allowed to escape, which gas will escape faster and how much faster will it escape? So typically what you would use is Graham's Law, right? We would use Graham's Law. Now there are no numbers in this. All we know is that we have helium and we have argon. So we can look up the molar mass of helium and we can look up the molar mass of argon, and that'll give us this here. But then again, it says, which one will escape faster? Obviously, we can predict that helium is going to escape faster than argon because helium is lighter, which makes sense. But then how would we describe how much faster? Right? So this is where we need to kind of use a little bit of logic. But here's what I'm going to say. I'm going to say R1, the lighter gas, is going to be representative of helium. Argon, I'm just going to set that to 1 because remember, I know that helium is going to be faster because helium is lighter. So if I set argon to be 1, this will give me the multiplicative of how fast it will be. And so again, molar mass of helium is 4. Molar mass of argon is 39.95. So when you do that, when you plug in x over 1 equals 39.95 over 4, and you take the entire square root, then what you end up getting is 3.16 meters per second, which means that if argon's moving at a speed of 1, then helium would be moving at a speed of 3.16. So that means that helium is 3.16 times faster than argon is. Now, Dalton's Law of partial pressure. So this is John Dalton. We may or may not have already talked about him, but he had a whole atomic theory and stuff. But he's really known mostly for pressure work. So John Dalton discovered that the pressure of individual gases must add up to the total pressure of the container, which means that if I have a container that contains, let's say, like 3 or 4 different gases, if I can find what the pressure of each individual gas is, that has to add up to the total pressure. And so typically, Dalton's law of partial pressure is written like this. PT, meaning the pressure of the total, equals the pressure of gas A plus the pressure of gas B plus the pressure of gas C, infinity, as many gases as you have in your container. So the thing that you need to be aware of, though, and why this is useful to us, is that most of the time when we're looking at gases, we collect them over water. And so what that means is if I have a chemical reaction occurring, I can pump the gas that's being generated into a container. And the way that I normally trap the gas is you have a container of water that now as the gas is being pushed in, the water level is going to drop, and now I have my gas trapped here. So here's a good example, right? We've got zinc and hydrochloric acid. Zinc is going to react with the hydrochloric acid and make hydrogen gas. So the hydrogen gas would be going out of this tube and go into this flask here. Now, the only problem with that is that we call this gas a wet gas because it includes the vapor pressure of the water. So since we have water here, the vapor pressure of the water is also in this entire container. So what John Dalton's law says is that if we have a gas that's going in, right? So let's say we have hydrogen again inside of here. There's also going to be some water vapor. So the water vapor and the hydrogen are going to be creating the total pressure of this system here. Now, most of the time you might think, okay, why is that a big deal? But really what we want is we want the dry weight of the gas because I want to know how much hydrogen there is, right? I don't care about the water. I want to know how much hydrogen there would be. So in order to do that, I would have to subtract the vapor pressure of the water from the hydrogen. And so I would take the total pressure and I would subtract the vapor pressure of water to get how much hydrogen there actually is. Now, what do we mean when we say vapor pressure? So every liquid that is going to be able to turn into a gas, right, over time, like by evaporation or something, creates vapor pressure. And so there's a whole chart of vapor pressure that we can look up, and it looks something like this. So this one is the one that's used typically for water vapor. You can see that it says the temperature is in Celsius here, and we have our pressure, which is in millimeters of mercury. So if you're wondering why we looked at all of those different conversions with pressure, it's specifically because we need to convert, to different units of pressure most of the time anyway. And so that would be a reason why we need to know that. So notice that we have increments of like 5 or 2.5, these are like where we would be if we were actually conducting an experiment. This would be kind of the range that we'd be in. Then after you get to a certain point, it just kind of goes by tens because, why are you going to be conducting an experiment when it's, the water is at, 40 degrees or 50 or 60 or 70 or at 100. Now notice at 100 degrees, the vapor pressure is equal to the atmospheric pressure because remember the atmospheric pressure is 1 atmosphere or 760 millimeters of mercury. And that makes sense because water boils at 100. So if it boils at 100, the vapor pressure is going to be equal to the atmospheric pressure. So again, this water vapor pressure table is just useful and it will be used in different types of questions. So this is just going to be our reference from now on pretty much. So here's what the application, let's say, of Dalton's law allows us to use. So we have mole fractions. Mole fraction is abbreviated as a capital X, and it's the ratio of the partial moles of a gas to the total moles of gas in a container. So it's like another way of looking at Dalton's law, but it's a little bit more useful because instead of looking at pressure, we're looking at moles. So now we're looking at weight. We're looking at, the mass of the gas itself. So here is how you find the mole fraction of something. So the mole fraction of gas A, let's say, is equal to the number of moles of gas A divided by the number of total moles in your container. And the reason why mole fraction is useful is because if we're looking at the total moles of gas in a container, if we add up all of the partial mole fractions here, we're going to end up equaling 1. Because remember, it's a mole fraction. So that means that we're really just we're basically kind of getting a percent. That's kind of what this fraction is. It's the percent of gas that's made up of gas A in the container. So since it's percent, that means that if you add up all of your percents, it has to equal 100, right? So if we're adding this up in fraction form, everything has to add up to 1. And so using mole fraction and using Dalton's law, we can use the combination of both to solve several different types of problems. So we're going to do just one example, but this includes all of that all together in one. So let's say I have a mixture of 40 grams of oxygen gas, 40 grams of helium. What would be the total pressure if, if it has a total pressure of 0.900 atmospheres, what is the partial pressure of each gas? So notice it gives me the masses of 2, and it gives me the total pressure in the container. So I need to figure out what that would look like for each gas. So great. Let's picture this as a mole fraction question and then also as a Dalton's law question. So first of all, I know that the number of moles of oxygen here and the number of moles of helium are going to add up to a total number. So I know that. I can find the number of moles by converting from grams to moles. So oxygen gas is O2. Helium is just helium. So I have 9.99 moles of O2. I have 1.25 moles of helium just by doing simple, let's say division, right? Now, total number, that means that if I add them together, I get 11.24 moles. So let's find the mole fraction, because remember, that will tell us the percent, let's say, of oxygen I have in my mixture and the percent of helium I have in my mixture. So oxygen, 9.99, the total is 11.24. It's 89% oxygen by mass. Helium, 1.25 divided by 11.24, that's 11% by mass. So if I know the total is 0.900 atmospheres, remember, Dalton's law says everything has to add up. So that means that I can find the partial pressure by taking my mole fraction and multiplying by the total. By doing that, 0.8 atmospheres of the 0.9 total is from just oxygen. And then if I do the same thing with helium, 11% of that is going to be 11% of the total is going to be the partial pressure of helium. That's just under 0.1. It's 0.099 atmospheres. Notice if I add these together, that adds up to the total pressure. Notice that if I add my mole fractions together, that adds up to 1. And that's how you would solve a question like that. Now let's take a look though at like water collection. Okay, so if we're collecting a wet gas. So nitrogen gas is being collected over water at 40 degrees. What is the partial pressure of nitrogen if the total pressure is 99.42 kilopascals? Okay, again, we got to think. I'm collecting it over water. So that means I have a partial pressure of nitrogen. I have a partial pressure of water. It has to add up to 99.42 kilopascals. And so I want to know, great, I need to subtract this partial pressure of water. So I need to look it up. Now, remember, our chart only gives us, millimeters of mercury. So I would need to convert some stuff, right? So if I look at the chart, it says 55.3 millimeters of mercury is what water's vapor pressure is at 40 degrees. I need to convert that, though, to kilopascals. So see if you can remember how to convert. But when you convert it, you should get 7.37 kilopascals. So now I can plug that in to here, and by simple subtraction, so by doing 99.42, which was my total, minus 7.37, which is my partial pressure of water, I can get 92.05 kilopascals as being my amount of nitrogen that was collected over the water. So again, this is wet and this is dry. All right, so if you have any questions, please let me know.